Welcome back to the exciting second part of de Broglie waves, of course. This is what we really came here for, right? Is these guys, right? This is a diagram of an electron microscope. This is a source of electrons, so that's just like a CRT. There's a hot filament here. There's thermionic emission and such, right? We accelerate them through a potential, and then there's lenses, and these lenses are probably in this case magnetic lenses, okay? And so the thing to keep in mind, though, is that the reason why electron microscopes are better than optical microscopes that use light is that you can remember light is, the wavelengths are 400 nanometers to 700 nanometers, right? This would be red light, that'd be blue light. Even if you're using blue light, remember that the image resolution is about the size of your wavelength, right? So with light, this is the limit of size of the object you can resolve. Electrons can have much smaller wavelengths. We just calculated accelerating potential for a 1 nanometer, right? That's much, much smaller than this, right? 400 times smaller than this. So that's why they have good resolution, is that you can make the wavelength smaller. Okay, it's like a computer screen with more pixels. Okay, and then yeah, they have electric. You can also use electric fields to focus these things. That electric field mapping lab you guys did, it's techniques like that back in the day that people used to map these electric fields and figure out how to focus the electron beams. Okay, until recently, we had a professor emeritus, a retired professor at PSU, who was a world expert in electron microscopes. And she was 80 years old when I met her back in the late 90s. She took me aside. My experiment wasn't working very well, and she took me aside and explained that experiments in science don't work a lot of the time. And I went into her lab and I saw one of these things. I mean, these things are just giant. This is a transmission. This thing here is a transmission electron microscope. Okay, and they are just giant things. Of course, you have to have a perfect vacuum in there. That's why it's stout like this, and it's got all these gaskets and stuff like that. The other kind that you're familiar with is scanning ones. These scan the outsides of things. So the pictures you see, if you see electron microscope pictures, they're almost always scanning electron microscope pictures. These are the sensational ones like this. These are, I think, smaller, probably more affordable. OMSI has one. If you go to OMSI, I think in the watershed room, they've got a scanning electron microscope, and you can stick things in it. I mean, it's really cool. Okay, these are the pictures you get from that, the sensational pictures of the outsides of bugs, and this poor guy here, he's got like drool coming out of his mouth. I always used to tell kids that these are the little parasitic bugs that live in the follicles of your eyelashes, but I'm just kidding. They're not. But there actually is some little bug that does live in your hair follicles. This is the skeleton of some microorganism that lived in the ocean. This guy looks like he's wearing a helmet. I don't know. I just like that guy. He looks kind of soulful, I don't know. This guy's got a newspaper. Look at him. I don't know. It's like boogers or something. It's cool, huh? Just do a image search for electron microscope pictures. Okay. I just put this one in here on a wild hare. This is some kind of hair. Hair is made of these little scales like that. And then the last one, the coolest microscope, is also the lamest. Okay. A scanning tunneling electron microscope basically is a probe. This little probe comes and it goes down, and when it just before it touches the surface, there's like a standing wave set up, a resonant condition, an electron tunneling current occurs, right? And it's extremely sensitive to this distance. And so they know exactly that they're exactly a certain distance above this thing. And so it's like they're making a map by just going doot, 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 right? It's so lame, right? It's an actual mechanical device that just sits there and measures this, right? Okay, and I don't know, maybe it can move pretty fast over that. They make images, right? This is the one that's made an image of DNA, right? When you see the images of molecules, of the helix, right? This is the guy that did it, okay? In Tualatin, they've got one of these things, and these things are like the size of they look like giant block of stuff. They have to be mounted on isolation tables because they're mechanical devices. They're literally, you float them on air. So this is like a couple tons of steel or something floating on a film of air to isolate it from the vibrations of people walking in and out of the room, right? At Novellus, they have these things. They put copper plating on chips to, you have to, here's your microchip, right, your silicon chip, and then you got to put a bunch of little wires to connect it to the rest of the circuit. Those things they put on atom at a time using copper plating, and they've got a scanning tunneling microscope to measure the thickness of the copper literally in orders of atomic diameters, right? I mean, it's just amazing, right? And it's in this room on this isolation table, and they didn't let me tour that because it's anyway, I wanted to see it. But anyway, very cool. So the final thing is, is light a wave or particle? And basically, this question here is doomed to failure. Okay, light isn't a wave, and it's not a particle, and electrons are not waves, and they're not particles, right? So to ask whether they are one or the other is wrong. Okay. The answer is that light and electrons, okay, small things, quantum objects, right, things that are governed by quantum mechanics, okay, are described by both, right? So this is the idea of complementarity, that you have to have both ideas to explain the concept of light. Light acts like a wave. It'll interfere, it'll diffract, it will do all these things that we know waves do, right? But light also does the photoelectric effect, right? Light can scatter off of electrons. This is called the Compton effect, right? So there's all sorts of evidence of light doing both things, right? So this is an idea of duality, right? So the answer to this question is it's neither. It's something that has to be described by both things. And then the question is, well, which description do we use? It depends on the situation. Okay, if you send light onto parallel slits like this, monochromatic light, it will make an interference pattern. It's going to act like a wave. If you send light onto a surface of a metal, little photons, right, it's going to eject photons as a particle. You tell me the situation, I'll tell you what it's going to do, right? And that's what science is about, right? Is deciding that, right? Now, the thing that's weird about this, and this is one of the things that Einstein didn't like so much, or would attack, right? He would try to bring this down, is that it tends to be, or what it is absolutely, right? It is absolutely an exclusive or. So if in a certain situation it's acting like a wave, it won't act like a particle. And if it acts like a particle, it will not act like a wave. It cannot do both. It is one exclusive or the other. And why is it exclusive or? Why can it only be one or the other? And the answer to that is that we don't know. Okay, it's just a rule, an inherent part of the universe that we don't know. We don't know. Okay. Well, there you go. Hope I haven't ruined your brain too much.